that was the technical roadmap for IonQ for a better part of the decade. This year, we hit our technical goal 7 months early, AQ 29. When we created this slide, we didn't have a lot of track record at that particular point. But now we've shown we can deliver, and more importantly, we can deliver early. AQ 35 on Forte and AQ 64 on a new barium system. So I show you this slide because in 2025, we expect to hit AQ 64. That will be here in a blink of the eye. So for us, all this work has come together to build this remarkable machine, and we expect it to be a better mousetrap and solve problems for our customers in the very near term. So I want to talk a little bit about AQ 64 and why we're so excited about it. You've heard from us and others that every time you add a usable qubit, that you double the computational power of the machine. So at AQ 64, that's equal 2 to the 64. You could type that into your browser right now and see what that means. But it's equal to 18 quintillion. I had to look up what that number actually meant because I'd never heard that before. So it means that in 2025, we will have a machine that is capable of exploring our computational space of 18 quintillion different states in a single instruction. So now we have to unpack what quintillion is. It's such a large number, and almost none of us have heard of it before. So I'll try to put this in perspective. If AQ5 was the tip of a marker, then that's what AQ5. AQ29 would be roughly, if I was to use AQ5 in that tip, would be about the size of a basketball court. And at AQ64, it would be larger than the landmass of the United States. So this is really the next machines which are coming from IonQ. Another way to look at it, just trying to look for places where you can see quintillion, is that at Oak Ridge National Laboratory, Frontier, the world's largest supercomputer, can calculate roughly 1.2 quintillion different floating point operations per second. So we're talking about doing 18 quintillion different computational states in a fraction of a second. Just for fun, the only other place I've heard this word was actually with Tom Cruise talking about in the latest Mission Impossible that it can consider a quintillion different possibilities. And so maybe quintillion in the human lexicon will become more and more popular going forward, although I wouldn't spend a lot of time there, because if you just add a couple more qubits, then you're going to need to learn the next thing after quintillion. And so, in fact, actually, we will very quickly get to a point where mankind has not come up with words yet for the kinds of numbers that we're talking about. Because at AQ 256, that's 2 to the 256. At AQ 120, the machine can consider the same number of possible states as there is atoms in the known universe, all 13.8 billion light years across. And at AQ 256, it's a number which is just unimaginable. And if you looked at our roadmap, by the end of the decade, we're talking about having 1,024 usable qubits. So it's 2 to the 1,024. And that's just a number, can't be calculated. Actually, that number, it can't be calculated on a PC today, just that one number. But my guess is if you could calculate that number, it would probably take something like 32 gig of RAM just to store the one number as to how big it actually is. So these are just unimaginably large numbers kind of going forward. So at AQ 64, this really is a huge milestone, not only for IonQ, but also for the quantum computer industry. When I started, what experts told me was that at roughly 65 to 70 good enough qubits, that's the kind of Goldilocks zone where suddenly quantum computing is really useful. At about 35 algorithmic qubits, you start to leave full simulation behind. And so now you're going to want to start to run it on a quantum computer rather than on a classical machine in doing simulation. And all of this is now not too far away. And we just announced our first sale of one of these systems, actually 2 systems, to Quantum Basel in Switzerland. So next I want to talk about how is it that IonQ pulled ahead of the rest of the competition. So, the very first thing is that we chose a qubit that Mother Nature provided for us. There is kind of in the quantum world, there's 2 different kinds of qubit modalities, one which is man-made and one which is using an atomic particle that Mother Nature. And so that's what we did. We're ions, and it's naturally quantum. It meant that we didn't have to tackle the problem of creating a man-made qubit. And second, we're piggybacking on mature technology on several areas, such as atomic clocks. Our ion traps and an atomic clock have a lot in common. And that is very mature technology that is being used in, with GPS systems and fairly common. Actually, an atomic clock is a chip nowadays that's only about 1.5 inches across and fairly easy, I believe, to get. So our ability to choose a technology, we've said in the past where we didn't need to have a breakthrough in physics, we didn't need a breakthrough in manufacturing, yields, material science, any of those things. That gave us a huge advantage, which allows us to be the first to this next phase of the market. The next big thing, which is people are going to start to realize, is the connectivity, and you already know fidelity matters more than physical qubit count. And so what you're seeing here is a picture of the connectivity of an AQ29 system, is that every qubit can talk to every other qubit directly. So you don't, and you can see on the other side, kind of a typical nearest neighbor system from some of the competitors. If you wanted to have this qubit talk to this qubit, you would have to use the intervening qubits in between to be wires. And you use an operation called a swap gate, and it happens to be one of the noisiest operations in quantum. And so you're basically using your qubits not for computation, but for connectivity. And this is not a huge issue when you have a small number of qubits, but as you get to a much larger set of qubits, suddenly this connectivity will really matter to you in a big way. And so we expect the world to start to realize that, especially developers kind of going forward, the advantage that we have. Of course, the second part is the fidelity itself, is ion traps. I don't think it's controversial at this point, is that ion traps have the best native 2-qubit, average 2-qubit gate fidelities in the market. And so that fidelity then controls the size of the circuit that you can run. And we'll talk about that as to what kinds of things you can do with AQ64 coming up as part of Dean's speech. So for me, this next section here is really interesting, maybe the big announcement of the day in some sense, is we showed you this slide previously, and it was based on a BCG data, and it talked about the 3 different phases of quantum. The very first phase here was the NISQ era, this noisy qubits that we were doing computation with. The second phase would be to have higher fidelities and to be able to get to using error correction. And so that would enable much larger programs, things like AQ64 to be able to happen. And we reported that we thought, we had shown that we have done error correction with an overhead of 1 in 16, meaning 16 qubits to get another 9 out of the average 2-qubit gate fidelities. But what's happened in the last 1.5 years is that we think that we have a good shot of getting to AQ64 without error correction. And that's really large for us. We're working on both an error-corrected approach and a non-error-corrected approach. We're working on both. And how do we think now that we can do that? Is in the last 2 years, we found something else called error mitigation. And error mitigation was basically a statistical approach to go through and find some of the systematic errors that are in the system and remove them before we deliver it to the customer. And so, and this was particularly important for our systems because much of the noise that you see in our systems comes from the control software itself. And so we can mitigate that through software. And so we don't know yet, but our intuition is that we can get here now without full error correction. And Dean is going to talk about that coming up shortly. So that allows us to enter this new phase. We're now talking about AQ64 in phase 2. And instead of calling it error correction phase, instead we're going to say that it's an enterprise grade error for quantum. Because at AQ64 is, we believe that now we can start to build that better mousetrap and deliver value to customers. So, and I think I have not heard personally any other company talking about getting to a point within the next 2 years where they will have easily manufacturable systems that have a sufficient power to be able to deliver real economic value to customers. Today, what you see in almost every case is proof of concept projects with enterprises. They tend to be small and low value. And we now are actually moving away from those things and now working on full-blown applications that will take advantage of AQ64. I mean, we're now only 2 years away from that. And this is just like any other software development. takes time. If we were going to go out and create a social media application, we decided all together we were going to create a company to do that. It would not be an unreasonable expectation that that would take a year or two to develop. And so we're just at that right phase now where we're starting to create software with customers that will take advantage of those systems coming up. So this is an exciting time for the company kind of going forward, especially in the next 2 years. You'll be hearing a lot more about this. And you'll hear about some of the applications that we're building today and the number of qubits required to be able to run them. So the next kind of thing that gives us an advantage is when we started the company, when I was first, I think there was 35, 40 employees. And Chris and Jungsang, myself, and a lot of students from Chris and Jungsang's labs were kind of the early employees of IonQ. Over the last 4.5 years since I've been here, we have been moving the company from an academic organization. We're proud of our academic origins, but we're moving to an engineering-driven organization. And you're going to hear from the leaders that we've hired in the last several years today. And you can kind of see some of their backgrounds, and they'll tell you about that as well. For the most part, these are people out of industry. We still have one more transformation to go, which is to go from an engineering organization to a product one. And so that's kind of the next phase, I would think, over the next several years for IonQ. One other advantage is we early on were available on all 3 clouds, and we're unique in that way. Having a customer meant that we had to build a product that met an SLA. Strangely, the cloud guys want this thing to run 24/7. Go figure. And so we had to be responsive to customer demands. And our customers have pushed us to build better products. They've made us a better company. But we aren't done yet. Without customers, though, we wouldn't be where we are today. And so that early first customer contact in our life cycle actually pushed us to build better products. When we first did the very first deal with Amazon, the computers would only run for a couple of minutes. And then they'd have to go into calibration. We famously joked at that particular time that you needed a bunch of physicists to turn a bunch of screws with some screwdrivers to get it to work. And I said to them, everywhere somebody out back turns the screw to calibrate the machine, I want to have a stepper motor there, and I want the operating system to control it. And I want it to be the one that's calibrating the machine. And so today, what happens is the machine is continuously calibrating. It's basically between jobs. It's going through and tweaking the machine, where 4 years ago, that was done by humans. And so we have made great strides in producing a product. I like to joke, no humans were harmed while we ran your particular job on our quantum computers. And that is increasingly so. We're not done yet. The next phase is actually to put these into customers' data centers. And of course, we don't want to have full-time people actually there working to be able to keep them up and running. So we're now focused very much so on how to be able to do that, and also how to do the next generation systems, how to do field support. Today, a power supply might be in the back of the quantum computer. If it goes down, I might have to tear the damn thing apart to be able to replace the power supply. So I need now in the future to make sure the things which are likely to fail, that I can easily go in and a field support person with limited knowledge could pull that part and can get a new part in. Okay, so another advantage to the company is that we have ever increasing revenue, and of course we get to apply that financial stream back to the product itself. And so it gives us an advantage compared to others who don't have these kinds of sales. And then, of course, everyone has talked about this, but we have quite a bit of cash. We have a large war chest. And this simply allows us to invest in ways that others can't. It allows us to hire the best, invest in building cheaper systems, more manufacturable systems, and that, as I mentioned, systems that can be supported at a customer site. And that's exactly what we're doing. People have asked us, with all that cash, are we going to be doing lots of M&A? We have done one transaction, and we're always looking for a good deal. But we're really focusing our resources on how to build cheaper and smaller quantum computers with our vendors. But to achieve this, just to be clear, it doesn't mean that we have to buy our vendors to be able to get to cheaper ones. So we're spending our dollars largely with things like paying for MRE with vendors to be able to get to a smaller, cheaper product. So the next thing, which you also already know about, is this is a picture of the Bothell facility. We signed the lease earlier in the year. Took a while to get building permits. You probably heard that before, especially if you own your own house. And we went through with architects and large construction firms, little things like reinforcing the roof with structural steel so we could handle the weight load of new air handling systems so that we can build a very clean environment to be able to assemble these quantum computers. So I'm proud to say that we are on budget and on time, and in this fall is we will start to take occupancy of the building and start manufacturing the next generation of quantum computers. And then the other piece that allows us to do things that others can't, because largely our cash position, is our expansion internationally. And so you can see here we did acquisition in Entangled Networks in Toronto. Of course, you're here in College Park. We just talked about Bothell. Bothell, by the way, is about 65,000 square feet. Just to give you a sense of scale, that's about twice the size of this entire facility. So just to kind of give you while you're traveling around today. In Basel, we will open up a small facility to be able to house the quantum computers and also Salesforce and application development for the European market. We opened subsidiaries in Germany and also in Israel and have started hiring there as well. So all of these things are possible because of our financials. So I just wanted to talk a little bit about the life cycle of the hardware products here. Is that at the very beginning, it's all about research and development. These are kind of the early lab experiments. Then you start getting customers who start pushing you to build better products. Then to get to manufacturing and get to a point where you can actually easily build these things. Strangely, little things like, can you build the same quantum computer twice? And do you have engineering change orders and all those kinds of things that real companies do? And then lastly is, can you support the product in the field? And so all companies have to run through this cycle, and IonQ is kind of I believe, the first that I know of that's actually doing exactly these things. So this is kind of that same slide that we talked with at the very beginning about the 3 different phases. And so we think that we're about to enter this enterprise grade area with AQ64 within roughly the next two years. And what does that mean? Well, it means that we're going to have first mover advantage. And you've probably seen this slide elsewhere in other markets that say that the first movers capture 90% of the value in any new technology. I believe there's been studies that show this. And so we think in quantum, for both our customers and for IonQ itself, that we will have first mover advantage. And then my last slide is just to kind of talk about where we think the company will be in the future. And if we're successful, I think IonQ has the chance to be one of the leading companies of our time. That if we do what we think we can do, that if we were to look 20 years down the road, that IonQ might be in the same class as many of these large companies that are the most successful companies today. And that's why we show up excited every day, and I think why our investors are investing in the company in the belief that maybe we have a good shot at getting there as well. So with that, I'm going to open up for questions. And then just to let you know, the rest of the day, I've kind of previewed what we're going to talk about today. But the rest of the day, there's going to be the experts who are going to dive in on things like how do we get to AQ64 and all the rest. So I'm happy to answer any questions, but you really are going to get a chance to meet the experts today. And then, for some questions, it might be better to ask them than me. So with that, I'll open it up for questions.
Sure, Peter, you touched on AQ64 and whether it will or will not have error correction. Which way do you think it goes?
I think it goes without error correction, would be my guess. But in everything that I guess maybe not everything, but many things we do out back, we're investing in multiple paths so that we have multiple shots on goal. So we're working on error correction just as much as we are without it, but I think the current belief is we can get there without it.
And would there be a difference in usable time if it's error corrected versus non-error corrected?
It's yes. I mean, error correction itself takes time to run, so it takes away from your computational time, which it would be better, but it's just easier. It would turn out to be a lot easier because I wouldn't need hundreds of qubits to put onto a chip. It means I would need only a little more than the 64 to be able to get there.
Got it. Thank you.
Any other questions? Then in that case, I'm going to turn it over to our next set of speakers. Thank you. In a few minutes? Okay.